Welcome and thanks for showing up today. I wasn't sure how many people would be here. I'm glad that it's greater than zero. My voice has been giving me trouble, so if you have any trouble, just cup your ear or something, and I'll just try to speak a little bit louder. So this is a temperature logger using a Raspberry Pi. Probably most of you don't need this, but you can use this as an example to see how much capability the Raspberry Pi has, and you might be able to relate it to another project. I have a slide at the end that shows an item that I found at Micro Center that has 37 different sensors on there, like sound and humidity and water and whatever. So maybe you'll have something that's similar to this, but not exactly this. Okay. So my wife and I live in a continuing care retirement community. There's a lot of them around. They all have are competing for clients, for residents, and they all have a lot of amenities. So you'll see, pools and libraries and fitness and garden plots and whatever. Ours has a greenhouse, which is something I haven't seen anyplace else. It's not a standalone greenhouse. It's on the fourth floor of one of the apartment buildings that has 4 floors, and it's at the top. So here's a picture from more or less the hallway, looking down into it. And you can see it's butted up against one wall, and then we have glass on the rest of it. Most of the freestanding greenhouses, they don't have any air handling in there, no heating, no cooling. This gets most of the use during the winter months. And we live in Sellersville, Pennsylvania. And of course, you would need some heat. We have heat in there. It still gets used in the summertime. We don't have air conditioning in there. But what we do have is up in this far top corner is an exhaust fan. It's about 3 feet in diameter. There's louvers on the outside, which open up when the fan is turned on. You can see that there's a lot of geraniums in here. There's some amaryllis. There's one resident who has about a dozen or 15 amaryllis bulbs, and he pots one up about once a week. So all during the winter, we have amaryllis blooming in there. You'll see other plants. There's the famous Irish one, the philodendron over here. It sometimes is even more full than this. There's a sink in there. There's potting soil. It's nice. You can leave the lights on till whatever, 9, 10 o'clock at night, and the plants seem to thrive there well. So let me go to the other end of the room, and I'm looking back now. You can see the door into the hallway, and here in this corner is the intake for air that will be exhausted by that fan. And this also has louvers on there so that when the fan turns on, the air pressure opens up and brings some air in. So during the summertime, when we've got lots and lots of solar heating, it won't take it below ambient, but at least it won't melt all your flower pots and so on. Up in here, this is a small electric heater with a fan in it. And there are 2 baseboard heaters below there. And those 3 items, the exhaust fan has a thermostat here. This is the thermostat for this fan, and this thermostat is for the baseboard heating. And they all have to be adjusted right. When we were having a problem, I would go there and the heater would be on and the exhaust fan would be on, and that isn't good. So what we needed is a temperature logger. Now, if you've been to a art museum or a historic home, you've probably seen one of these. There's a metal plate in the back that's connected to a a motor that turns once every 24 hours. This paper scale is put on top of there and rotates with it. There is a little arm here that pivots at this area, and it moves according to the temperature. At the end, there's a little ink reservoir with a point on there so that that moves in and out depending on the temperature. The back turns, you run it for a day, and it gives you a record of what the temperature was in there over the preceding day. So we don't have one of those, but the electrical engineer says I can do this with a Raspberry Pi. So if you're not familiar with the Raspberry Pi, there's a number of different types. The smallest one is you can get for under $10. The newest one is a Raspberry Pi 5. I think the top of the line is around $100. This one is a Raspberry Pi 3B, which is a couple of years old. And just to show you what's on there, this is it. You can see it's about the size of a deck of cards. And over in this area, we have 4 USB ports. We have a wired Ethernet jack. On the 3B, it only went up to 100 megabits. The 3B plus, and from then on, goes up to a gigabit. There's a jack here, which gives you audio in and out, and also composite video. There's a connector for a ribbon cable to go to a camera. There's a full-size HDMI connector. There's a micro USB connector that goes to your power supply, regular like phone charger size. There's another ribbon cable connector to go to a display port. And on the bottom is a micro SD card slot to put a micro SD card in there, which will then serve as our storage for operating system data and whatever else. In the back here is a 40-pin general purpose I/O connector. You can program the pins to be input or output, to have pull-ups, no pull-ups. They sell things called abbreviated hats, which will plug on top of there. The newer one for the Raspberry Pi 5 has an M.2 connector, so you can put a lot more and more reliable storage on there. There's all kinds of these. There's little miniature touch screen if you just have a little bit to display. And what you don't see here is Bluetooth and Wi-Fi on there. The processor is here. It is a Broadcom ARM 4-core. It's got 1 gigabit byte of RAM on there. We already talked about most of these others. Okay, so you can buy SD cards from different places that already have an operating system put on there for you, but I like to do it myself, of course. And so you can start out with a blank SD card. So to get this thing configured, there's some things you'll need just only while you're installing them, as you might expect, a monitor, keyboard, and mouse. I think they might have it so that you could use an SSH client to get in there and not even need these, but I have them available, so there we go. And of course, once we get it set up, we're going to be running this thing headless with basically just standalone like this and just plugged into power. This is what the typical power supply would look like. There's all sorts of cases, metal, wood, plastic. This is from a company called Adafruit. Actually, I guess that's this one, but this is a slightly different color. I'm using a Samsung 32 gigabyte micro SD card. Most of these come with adapters that will make them full size. I then plug that into an adapter that goes from there into a USB connector to plug into my PC to actually do the loading and getting it ready to boot up. So Raspberry Pi has a nice utility on their website, an imager. It's got 3 choices here. So the first button here, you'll pick what your target device is, which Raspberry Pi you're going to be aiming for. So it gives you a lot of choices here. You can see this one is set up for a Raspberry Pi 5 on down through Raspberry Pi 0, and the oldest one's Raspberry Pi 1. Since this is a 3B, I'll choose this one in the center here, Raspberry Pi 3, which covers the BEA+, B+, and a Compute Module 3 and 3+. The second button on there lets us pick which operating system we want to put on that SD card. What's recommended is the first one at the top, Raspberry Pi OS. It's based on Debian Bookworm, which is I think the latest Debian version, and Raspberry Pi desktop on there too. But you can pick other ones depending on what you want. Stripped down ones, older ones. They even have other ones that you could put on there. Here's one for media player, and if you expand this, you'll see some other choices. The third button on that imager gives you an opportunity to pick where you're going to store this image. And I had this plugged into my Windows machine. You can see it's 31 gigabytes usable space on there. And once you get this all set up and hit it to start, then it will download it, put it on there. When it's finished, you can take the SD card out, plug it into this little socket on the bottom of your Raspberry Pi that's ready to boot up. I'm not going to spend any time on what that process is because they have such great tutorials at raspberrypi.org, and you can find other ones on YouTube too. It sets up things like which device interface you want to use, wired, wireless, get a username, on and on. So when we were talking about the capability of the device itself, you notice I didn't mention anything about a temperature sensor. So you need to get something and mount it externally. So this thing is about the size of a very small postage stamp, and it's mostly just a carrier for the actual sensor, which you can't see, but it's about maybe a third of the size of a grain of rice on here. We're going to get into the data sheet, and you'll see how capable that thing is. That this little daughter board here is basically just a way to bring the 6 pins from this little sensor out to pads. You could solder 6 pins on here and then put jumper wires, plug it into a breadboard, and then jumper it. I've soldered wires right to those pads, and then you'll see that we're going to put it on top of our general purpose I/O connector. So a little background here. To talk to this guy, it's a digital sensor. We're going to use this SM bus, system management bus. It's a 2-wired interface. It's got a data line and a clock line, goes in and goes out. You can have multiple devices. I only have the one here, and it's based on this I2C protocol, which has been around for a while. It was developed by Philips, and you'll see it show up in a lot of places. So this Zagros Robotics is the company that makes this little daughter board. The sensor itself is from TI, and you can see a slightly bigger picture here. It's about $5, $4.95 from them, plus shipping. And this is what it looks like. You'll see there's a couple resistors, a capacitor on there, plus the sensor itself. This is the schematic for it. And you'll see that those 6 pins, we've got power and ground. We've got this SDA, for data in and out, and SCL is the clock line for that. It's got one address line. You can use this to pick one of 4 addresses on here, 48, 49, 4A, or 4B. And then there's an alert line. We're not going to be using that in our little project here today. All right, let's look at the data sheet and be amazed here. It's in this SOT 563 package, which is, again, about a little bit less than a millimeter on each size. It's accurate to 0.5 degree C from minus 25 C to plus 85 C, which is pretty good. It needs 1.4 to 3.6 volt, not 5 volt, as a lot of devices need. It's got a 12-bit A to D converter in there and digital output. So it's sold for some of these applications. You can see that it would be useful in thermostats, office machines, computers, notebooks to tell when to turn the fan on and so on, and other test equipment and so on. There's a block diagram down in the corner. You can see it packs a lot in there. This is another view of it with its typical connections, with what the registers look like, and down at the bottom, how to talk to the different registers. We go to the next screen, we'll see what the temperature register itself looks like. So it's going to end up in a 16-bit word, but it comes out in 2 8-bit bytes serially. And with a 12-bit product there, we're going to use all 8 bits of 1 byte and then 4 bytes of the next byte. So 8 bits plus 4 bits. At the bottom is a chart of what the format looks like. So all zeros on those 12 bits, 0 degrees centigrade. If we get 1 bit up, and you can see it's the lowest bit on here, not counting those 4 bits of zeros. That's going to be a 1/4 degree centigrade, and so on up to its maximum and down to its minimum. They also have a 13-bit mode. We're not going to use that. There's some other options on there in the bottom right. You can see that we can set the conversion rate. It defaults to 0.25 per second, or 4 times a second, and we're just going to leave it there. But if you had a different reason, you could set it up to one of those other rates. All right, let's look at that GPIO connector in more detail. Here's what each of those 40 pins are used for. And you can see that we have all the general purpose IO pins come out here, along with a lot of ground pins and some power pins. It makes 5-volt power available, but we can't use that. It would damage that sensor on there. But there is a 3.3-volt power up here. We're going to use that. And you'll notice that GPIO 2 and 3 have a parenthesis SDA and SCL. So those are the 2 that we're going to use for clock and data on our little sensor here. Okay, so I already showed you that I have jumper wires put on there. This is a little blow up of what you can't see from where you're sitting, but this is that plus 3.3 line. This is the clock line. Maybe it's the data line. I have to go back and look, but this is data and clock. This is a ground line. This is connected to the address line to make our little device here answer to hex address 48. And then the ground line at the back is the ground line for power for it. So you've already seen, let me hold this up. That's kind of a blow up for you. I do have a fan mounted on the top of this. I don't use the fan when I'm using this, but if I'm using it for something else, I generally have the fan connected. It does get a little warm in there. Not too warm, but I think heat is the enemy of all electronics, and I like to keep it cooler if I can. So once we have taken our SD card and configured that and plugged it in, and we have this plugged in, we need to do some more configuration so that we can access this. So we're going to have a Python program. Maybe some of you are familiar with it, but don't worry about it. It's mostly English. We have to do some editing to be able to talk to this little sensor. So you may or may not need this. I did when I first used it, but I think maybe a later version might have it already configured. So we're going to go into this file, and I have the location at the top. Nano is an editor that runs on here. This is the, should we get rid of that? This is the location of this file, Raspberry Blacklist. And when we start, this file will probably have a pound sign in front of this first line. And the pound sign in this file and the other files make the line a comment. So it would be commented out. I'm sorry, would not have a pound sign on there. They're both going to blacklist these so they would not get used, but we're going to comment the second one out so that this I2C connections in this module that we're going to be using is available for us in our Python program. So like I say, you may not need that, but load it up, see it. If you have to comment it out, then comment it out. Next thing, we have to go to this file, config.txt, and we have to add these at the bottom, add these two parameters. We have to turn the I2C clock on and enable this also. Again, it might be there, probably isn't there. Add this, save it, and then move on to the next one, which is going to be which modules we're going to load. Now, this package typically only loads this. We're going to add these three lines at the bottom. This is a set of Python functions which will function with the Broadcom CPU that we have in there, and then to function with a device that's using that. So not only this temperature sensor, but other ones. Some other things we should do is these four. So we're going to use this apt-get install i2c-tool. So this is a package on the operating system that will load some tools for us. We're going to use one at the end in this fourth line down. We're also going to install Python 3-SM bus, which is another set of functions which will let our Python program talk to the SM bus and then talk to our sensor. We're going to add another user, Pi, which we configured when we did the original setup, to a group called I2C, and that's so we have privileges to talk to this. And the fourth line up here is I2C detect -y -1. So this is one of those utilities, and what it's going to do is go out onto the available addresses in this I2C space and see what is going to answer to us. And when I run that, it's going to run from 0 hex all the way up to 7 hex, and the only one that replies is at 48, which is what I hope to see, because that's what we configure this. So this should give you a warm fuzzy when you see that. So this is just a tool to make sure that things are going well so far. We've got the modules in there that we need to be able to access this. All right, so we're going to get into our Python program now. And this is, I've taken and made 2 columns out of this so I can fit it on one screen. Again, if you're not familiar with Python, this should make sense to you. So the outline of this came from Zagros Robotics, which is, if you remember, the place that I bought this little board from. They had it in there available as a sample, and you can, of course, change it any way you want it. So the first thing we're going to do is we're going to put these 3 import lines. So import in Python says, go out to a library and get some packages of functions that we're going to end up using later on. So we're going to import SMBus. Again, that's going to let us use that to our data transfer. We're going to import time because we're going to know what time we're going to take our measurement. We're going to import date time, which is going to let us format that. And time gets it in Unix epic format, and date time will let us get it into machine English format. Here's 2 comment lines. And we know that because there's pound signs at the beginning. And it's telling us to use SMBus1 if we have a Pi model B or later. If you have the older one, you want to use SMBus0. And so that in this next line, we're going to create an object called bus. We're going to call this function SMBus, which is part of this SMBus package that we loaded. And we're going to give it one argument, the number 1. That's going to configure this to work with our Raspberry Pi 3B. The next line is a comment that says that we need to set up the address of the sensor. You'll recognize 48 now, hex 48. We're going to store it in a variable called address. The next thing, we're going to take 6 lines and define a function. So this function is going to be called temperature. It's going to go out and get a reading from our sensor and then return that to us. So the first thing we're going to do is we're going to do a bus dot read underscore word underscore data. Again, that's part of this bus package that we loaded right here. This is the object that's saved. This is the function that actually does the read. It's going to read it from this address that we set up, 48. And I forget what the second argument is, but this is going to get a 16-bit word in there. We already know that this has only 12 bits of interest. So we're going to take this R value 0 that we got in. We're going to extract off the top 8 bits. We're going to then shift it right 8 bits. And we're going to store that in this R value 1 variable. We're going to go back to what we got in from R value 0. We're going to mask off the bottom 8 bits, and we're going to store that in this variable R value 2. Now we're ready to compute what the actual temperature is. We're going to take R value 2 and we're going to shift that left 8 bits. So I could have done a shift, but instead I multiplied it by 256. It's the same thing. And we're going to add in the lower bits, which we've shifted right. So if the thing had returned the 16 bits in the right order, we wouldn't have to do this junk, but we do. So once we get it in this form, inside these parentheses, we now have a 12-bit value that agrees with that table that we saw in the spec sheet. And we're going to multiply that 16-bit number by 0.625, which is the value for one of those bits. This is in degrees centigrade. Once we have that computed, we're going to return from our function. We're going to return that variable. So every time we call the function temperature, we're going to come back with a digital temperature in degrees centigrade. So now we're actually going to do something. We're going to print out to our console this string which says temperature data logger followed by a new line character. And we're going to start a while loop. So a while loop says, take the next block of data, keep doing that as long as this next variable is true. So ordinarily it would be, if today is Saturday, if your name is Don, if, whatever. We're going to say while true. Well, is true ever false? No, it's always true, which means that once we get in this block, it's going to run till the cows come home, right? And that's what we're going to do. The only way it's going to stop is if we yank the power cord out or get access to this and then tell it to stop. All right, so in Python, blocks are denoted by indentation. That's what we did here in the function for temperature. We indented this. When we finished indenting, we were done with the function. In our while block, this is all indented down here. This line ran over, so that's why it looks like it's not indented, but it's actually is indented. And the block looks like this. So here's a comment. We're going to open the log file. So we're going to use an open statement to open a file with this name, tempdata.txt. We're going to open it in append mode. So append mode means if the file doesn't exist, create the file, position at the beginning of the file. If the file already exists, we're going to open it and we're going to position at the end of the file, ready to add something to it. When we do that, we're going to store that file handle in this variable f. Next, we're going to get a variable now, and what we're going to do is call datetime.datetime.now, which is our method to get the time of day, and it's probably going to be in Unix time. And so we're going to have to use this string from time function. This is a format which says we want to take that Unix time and convert it into 4 digits for the year, a slash, 2 for the month, a slash, 2 for the day, a space, 2 for the hour, a colon, and 2 for the minute. Once we have that string, we'll store it in timestamp. We're then going to get a variable out value. We're going to call our function temperature, doesn't need any arguments. When it returns, it's going to have our temperature in degrees centigrade. We're going to come up and make a new string variable. We're going to concatenate timestamp as a string. We're going to follow that by a comma. Then we're going to follow that by a string and with a new line. So that string is going to be the out value, which is our temperature in degrees centigrade. We're going to multiply that by 1.8 and add 32. So we're converting that to Fahrenheit because we're in America and we don't speak centigrade here usually. I'll then do a print statement on this out string. It's going to put that on the console. I'm going to also write that to our file. It's either going to be at the beginning of the file if we just created it, or it's going to add on to the end, and then we're going to close the file. So we've added one more line with the time and the temperature on there. We're then going to call this sleep function for 60 seconds, which is going to just do nothing. It's going to wait for a minute. End the while loop, go back, while true, it's true, go through the thing again, and there we are. So pretty simple, right? You don't speak Python, it made perfect sense to you, right? Okay, so as I said, this is going to run forever. We have a problem here. We have two problems, right? Number one, we have to get it started. Number two, we have to get it stopped at some point. Now, I will tell you from bitter experience that if you interrupt Raspberry Pi while it's writing to your SD card, it's probably going to corrupt the file, and you're not going to not get any data. You're not going to have any operating system. You're not going to whatever. So it's a really, really bad thing to just pull the plug out. So we don't want to do that. So, which also means if you are going to put this someplace remotely, you might want to power it from a battery, like a battery backup system or something like that, just to make sure that that doesn't happen, especially if it's important. So we still have starting it and stopping it. Well, there's some different things we can do. Number one, I said we only need to have our monitor, keyboard, and mouse for setup, but you could keep those with you when you then go to your remote location, power it up, it'll start up, and you can then log in and you can start running things and so on. Another thing you can do is to connect this to a Wi-Fi if you have it available, or a wired network available. That way, when you plug it in, it'll start up, it'll show up on the network. You can either use VNC, which is gives you a GUI access to it, or use a secure shell client to get there and start it up and then stop it when you want. You'd hit a Control-C, which would be a clean shutdown on this, and then do a Raspberry Pi OS shutdown command, which is going to do a clean shutdown, and you won't mess up your file system. And there's another one I'll cover at the end, but it's kind of a variation on that. All right. So let's suppose we don't want to do that. We don't want to take the monitor with us. We don't have any room. For starting it, we can do the following. We can edit this file called rc.local. I think that's in your home directory. And we can put a command in here to start Python, point to the Python file. This doesn't have the same name, but that's just because I called it something different here. And to save the output and so on. And right at the end, this little ampersand tells it, do this command, but don't actually wait for it to finish. Normally, give a command, it does it, whether it's a print, whatever, finishes up, and then it returns to console or your script or whatever. But the ampersand says, start it, we don't care about it. And that's good because we already know our little program is going to run forever. So that'll get it started on its own. So how are we going to stop it? Well, we're going to, let's see, I think I have that code down there. All right, let's come back to stopping it. Eventually, you're going to get access to this file. It might be because you pulled this out and put it in your adapter and then into your PC. It could be because you plugged it back into your home network and you secure shelled in there, whatever. But at some point, you're going to get this file. So this is just a portion of one of them. You can see I ran it last month. And this, I wrote it this way because this is a CSV file format. And I want to do that because I want to load it into Excel. So I've loaded it into Excel and changed the format somehow. So this is just the hour and the temperature. And then I've used Excel plot mode to generate this. So this is a couple of years old, but I just happen to have this available. So I thought it would look good. So at the bottom, this scale is time from midnight to midnight. Here's the temperature in Fahrenheit from 60 to 100. And I've got it labeled with the date up here. So let's see what's happening. So this is in March. It's about the same time of year, a little bit earlier. We're at midnight. We see this kick in and get a little bit warmer. Well, that's that little fan, the little electric heater and a fan. So it warms it up a little bit, shuts off, trips on, goes on. So you can see that bouncing back and forth. In the morning, the sun comes up, hits the glass, starts to warm up in there. Eventually, it hits the thermostat for the fan, opens it up. It's still nice and cool outside, draws in that outside temperature. It goes way down to almost 60. The fan shuts off. The sun warms it up again. The fan turns on and turns off. We come up here. Again, the sun is up now, and we can see some, maybe there's a clouds in front of, in the glass, whatever. This is it's pretty sensitive. So I wouldn't be surprised if that's what that was. And then the sun goes down and the heater goes on and warms it up. And then the heater goes off and it slowly cools down. Here we get about 8 o'clock and we get back into that same mode again. So this was a sunny day, this Monday, and I got the outside temperature from the Weather Bureau, and you can see at midnight we were about the mid-30s. Kept cooling off till the sun came up. It got up to mid-60s in the afternoon, and then when the sun started going down, we cooled off again. I didn't get all the way down, but that's basically what we saw from the result. Then 2 days later, it was a cloudy day. This is Wednesday. You can see that we got a little solar heating in this area, but not enough to really warm it up. And this is just that one heater cycling on and off for the whole 24 hours. And this is the Weather Bureau temperature for that day. You can see it never really got up to 60, even in the afternoon. So that's what it does. I'm going to show you, this is a secure shell client that works on Android. If you have an iPhone or an iPad, you can probably find one in the App Store for that. And this lets us access our Raspberry Pis over the network, no matter where it is, as long as it's connected. I use Putty, which runs on Windows, Linux, and Apple, I think. And I use that from my PC to access these. If you need to transfer a file, you can set it up. This is FileZilla, which is a secure FTP app that runs on mostly everything. And I don't have it connected here, but that's a way to get it. What time am I done here? How am I doing on time? Okay, good. That'll be just fine. Okay, so I already talked about stopping and starting it. I covered the first three, well, the first, the third, and the fourth, but Raspberry Pi has added a new thing called Raspberry Pi Connect now. And the way that works is you get an account on raspberrypi.com, and it's a free account. And once you sign in with that and get the account created, you can then take that back to your Raspberry Pi and access that and sign that in with the same account credentials. And then as long as this is on a network, this will make a connection up to raspberrypi.com, and you can access it from whatever you have up to there. And it serves as a middleman so that you can make a connection, even if you can't get this on the same network. So where we are, there's a network in the building, but they use a thing called client isolation, which means that no two clients can see each other, although they can see the router and go out to the internet and whatever. But once you have that connected, the next time you log into Raspberry Pi Connect with your PC or whatever, you'll see Raspberry Pis that have logged in with your same credentials, and then you can either get a GUI connection to it or use a remote shell through them and get access to it. So this is yet another very convenient way to get access. And as far as stopping it goes, if you have to do it in a standalone mode, I should have oriented this earlier. These lines here will can be included in that Python program. If you start right under the other imports, this is to import a package that will let us access the GPIO connector, and also a package that will let us access the operating system. And we're going to do three things. We're going to set this mode to use Broadcom pin numbers. We're going to set up pin 12 to be an input, and we're going to connect a pull-down resistor to that. And then we're going to define a function, just like we did in the main body, called shutdown, and it's going to call the operating system function called shutdown, and this will make a clean shutdown. So how is this going to get activated? We're going to call this add event detect function, which will say, keep an eye on IO pin 12. When it falls, do a callback to this shutdown function, and bounce time we don't have to worry about. So how are we going to make that fall? Well, this is connected to the pin 12 on there, and all I have to do is ground this. So you could get a little switch and wire it up to 2 pins, and then hook it from pin 12 to a convenient ground. There are several of them on here. And then as long as you have that auto start in there, it'll start up when you plug it in. And when you hit this switch, it'll cleanly shut down. And like magic, there you are. Then you can, when it's shut down, you can disconnect the power, take it back, and do whatever. So I have a couple of links here for you, raspberrypi.com. I can make this available for you. We've seen all these. I mentioned this package of sensors. I have not purchased this, but you can see there's all sorts of sensors in there. And, you know, if you need to detect something, you can probably find it there. I have this slide set available as a PDF at this location. So if somebody wants to try it now, that would be good, because I didn't get a chance to do that. So if you want to look and see, make sure it's there. Any questions